morning. Today I'm going to talk about a groundbreaking approach to recycling one of the most challenging class of materials in the waste stream, fiber-reinforced polymer composites, or simply composites. Composites are heterogeneous materials. They are made of an organic polymer matrix and some reinforcing fibers coupled together. The matrix often consists of thermoset resin like unsaturated polyesters or epoxies, which form an irreversible cross-linked network during the curing process. The reinforcement, mostly glass or carbon fibers, provides high mechanical stiffness and strength. These materials are widely used in aerospace, automotive, and wind energy industries. They are incredibly strong and lightweight, resistant to corrosion, but really difficult to recycle due to their intrinsic multi-material structure. The standard technology for composite recycling are nowadays represented by mechanical and thermal recycling methods. Mechanical recycling involves grinding composite parts into shredded particles, but in this way the fibers are shortened, diminishing their value. Moreover, contamination by resin residues further limits the possibility of reuse. Using this method, fibers are never completely liberated from the matrix. Thermal recycling, like pyrolysis, breaks down the polymer backbone and evaporates the decomposition products at high temperatures to recover fibers. However, the heat treatment degrades glass fibers and can oxidize carbon fibers while generating dangerous emissions. Moreover, the organic fraction is often lost or only partially recovered, making this method not fully compliant to the principle of a circular economy. In general, both these two methods fail to reclaim high-purity monomers or intact fibers. Chemical recycling by green solvolysis in mild condition is an innovative and promising technology that instead not only recovers valuable materials but also aligns completely with the principle of a circular economy. Green solvolysis is a chemical recycling method that uses sustainable solvents and mild process conditions such as relatively low temperature and atmospheric pressure to break down selectively the polymer backbone into original monomers or oligomers with a controlled stepwise process. This process involves first a solvent selection. Each polymer is characterized by a solubility sphere. Green and bio-based solvents internal to the sphere boundaries, like some alcohols or glycols and organic acids, can be selected and used in combination with specific catalysts to enhance reactivity. The solvents will show a high thermodynamic affinity and swelling capacity of the polymer network. Second point, mild condition. Unlike pyrolysis or gasification, which require very high temperature up to 300 to 800 degrees C, solvolysis may operate at temperature around 150 to 200 degrees C and atmospheric pressure, making the process energy efficient and environmental friendly. The choice of the right catalyst is crucial in order to reduce the temperature and time needed for the process. Third point, the reaction mechanism. The solvolysis mechanism is essentially a swelling followed by controlled depolymerization by a stepwise mechanism, and it is specific for the different resin types. The solvent attacks some of the polymer chemical bonds, breaking it down into smaller molecules. Now, let's look at some examples. Chemical recycling by solvolysis of thermoset polymers is particularly challenging, but its development is essentially for achieving a circular economy, because thermosets cannot be remelted or reshaped like thermoplastics. Below, I'll explain some of the processes that can be adopted for the chemical recycling of the most important types of thermoset polymers used in composite manufacturing, that is, unsaturated polyesters and epoxies, which in turn can be cured with both amines or anhydrides. Unsaturated polyesters. Well, unsaturated polyesters are polyester oligomers containing some carbon double covalent bonds in the main chain, diluted with styrene as reactive solvent, and cured by a free radical chain process. They are mostly used in glass fiber reinforced composites, for example, for the naval or construction sectors. Their cross-linked structure makes them difficult to recycle, but the chemical methods like an acidolysis catalyzed by Lewis acids can break selectively the ester bonds, dissolving the organic matrix and releasing the glass fibers intact. Epoxy cured with amines. Epoxy resin, when cured with amines, are commonly used for carbon fiber composite manufacturing, for example, for the aerospace sector. The amine-cured epoxies have very strong covalent carbon-nitrogen bonds, which again can be selectively broken by catalyzed acidolysis with the liberation of clean carbon fibers. Then, epoxy cured with anhydrides. The same epoxy can be alternatively cured with anhydrides, and these matrix materials are often used in association with glass fibers, for example, for wind turbine manufacturing. The anhydride cured epoxies form a polyester network, which can be efficiently solvolyzed by glycolysis in presence of a transesterification catalyst. In all cases, the solvolysis process can be carried out at temperature around 20 degrees C and atmospheric pressure. Green solvolysis might offer several advantages in line with the expectation of the circular economy and composite recycling hierarchy. First, it allows an effective fiber liberation. The recovered fibers are intact, clean, and retain up to more than 90% of their original modulus and strength, making them fully reusable in composite remanufacturing. The purity of the fibers can be assessed, for example, by electron microscopy or by thermogravimetric analysis. The retention of mechanical properties can be assessed by microtensile testing of the single fibers before and after the recycling process. As a second point, it also allows the monomer recovery. Since the depolymerization process is controlled and not leading to an excessive randomization of the reaction products, also the organic recyclate is potentially reusable according to different closed-loop or open-loop pathways. It can be easily purified, for example by distillation or crystallization, and repolymerized into new resins, closing the loop in the material life cycle. For example, the organic recycled fraction recovered from the catalyzed glycolysis of the matrix from a wind turbine waste can be reused as a binder for the production of new transparent polyurethane coatings. Third point, energy efficiency and environmental impact. Catalysis allows to operate at mild condition and reduces energy consumption compared to thermal recycling methods like pyrolysis, which require much higher temperatures. Moreover, green and atoxic solvents can be used. They can be fully recovered by distillation at the end of the process and used again and again several times. Solvolysis avoids toxic emissions and reduces waste, contributing to a true circular economy. While solvolysis is a promising technology, it is not without a challenge. Solvent recovery, efficient separation and reuse of solvents are needed to make the process economically viable and circular. And this can be a challenge when using complex solvent mixtures. Second, process time optimization. Long reaction times might be necessary in case of very thick composite parts and very high TG polymer resins. Third point, scalability and economic viability. Scaling up solvolysis for industrial application requires optimization of the reaction condition and equipment. However, the ongoing research is addressing these challenges. For instance, new catalysts are being developed to improve reaction efficiency, and advanced separation techniques are being explored to recover solvents and monomer more efficiently. Additionally, integrating solvolysis with efficient energy generation, like microwave heating, for example, could further reduce its environmental footprint. In conclusion, green solvolysis in mild condition represents a transformative approach to recycling fiber-reinforced polymer composites. By recovering high-quality fibers and well-defined monomers, this method not only reduces waste, but also creates a sustainable pathway for reusing all these valuable materials. As we strive toward a circular economy, technologies like solvolysis will play a crucial role in reducing our reliance on virgin resources and minimizing the environmental impact. Thanks for watching.